I want you to think about just a giant problem for a second. How do you figure out what millions of people really think? I mean, about a new video game or, a new car or even just a new flavor of chips. You can't call everyone. You absolutely cannot email or interview every single person in the country. It would take a lifetime. And it would cost, well, more money than anyone has. So researchers needed a trick, a kind of superpower to shortcut the whole thing. And that trick is called sampling. Sampling is how researchers learn about a huge group, we call that the population, by only studying a tiny, really carefully chosen smaller group. That smaller group is the sample. The sample is supposed to be like a perfect snapshot, a mini version of that entire population. So our mission today is to show you that while this saves a ton of time and money, getting that snapshot right is, well, it's a huge challenge. A bad sample gives you bad information, and then suddenly you're canceling a hit show or, releasing a chip flavor that nobody actually likes. So let's figure out if we can trust the numbers we see every day. Before a researcher even thinks about picking up a phone, they have to draw a circle around exactly who they care about. This is the first and maybe the most crucial step, defining the target population. And you can't be vague about it. If you just say, I want to study teens, that's way too broad.
Way too broad. Are you talking about teens all over the world or just in your city? Teens who play sports?
Right. So scientists have to be super specific. They might define their population as, say, all registered voters between 18 and 25 living in California.
Exactly. The more specific you are about age, location, and all those other details, the more useful your study actually becomes.
Without that focus, the data you get could be confusing or just totally useless because you don't really know who you were measuring in the first place.
And once you have that big target population defined, then you pick your smaller group, the sample. And the number one rule, the foundation of all good research, is that this sample must reflect the diversity of that big population.
So if the big group is diverse, the small group has to be diverse in the exact same way.
Precisely. And that's where the science really comes in. We have these specific methods to fight against what we call human bias.
Bias, you mean like the instinct to just ask people you know?
Yes, or people who are easy to find or who you think will agree with you. The gold standard for fighting that is random sampling.
Random sampling. Okay, so what does that actually mean?
It's based on one simple but really powerful idea. Every single person in that target population has an absolutely equal chance of being chosen.
So wait, if my target population is every high school student in Chicago, you're not literally putting millions of names into a giant hat. That sounds impossible.
Haha. No, not a literal hat anymore, thankfully. Think of it more like a massive automated digital raffle.
Okay.
Researchers use computer programs to generate truly random picks from databases, like phone lists or voter registries.
And the benefit there is that the researcher has no control.
Zero control. It stops them from handpicking people they think might give them the answer they're hoping for. When it's truly random, it's highly respected. The laws of probability just tell us that it's very likely to represent the whole group fairly. It's the purest way to get that snapshot.
Okay, but what if you're worried about missing smaller groups? Just by, the luck of the draw.
That's a great point. Sometimes pure random chance isn't quite enough. And that's when we use a more organized method called stratified sampling.
Organized how?
Okay, imagine we're studying what 13-year-olds like to do for fun. And let's say we know the population is 75% console gamers and 25% who only play on PC.
Right.
If we just did a pure random sample, we might, just by chance, end up with way too many console players and not enough TC players.
So you wouldn't get a balanced view.
Exactly. So with stratified sampling, researchers first divide the whole population into these smaller subgroups, which we call strata.
So you'd have a console gamer group and a PC gamer group.
Perfect. And then you take a separate random sample from each of those subgroups.
So you're basically forcing yourself to pull 75% of your sample from the console group and 25% from the PC group.
You got it. The goal is to balance the view to precisely match the real population. It makes sure that those smaller groups aren't accidentally left out.
That makes perfect sense if you're trying to be fair and accurate. But let's be real, that sounds like a lot of work.
It is.
So what happens when researchers are short on time or money or maybe are just a little lazy? This brings us to a method that is fast, it's cheap, but it is absolutely full of danger. Convenience sampling.
Mm-hmm. The danger zone.
This is where researchers just pick people who are easy to reach. The classic example is a student doing a poll by interviewing friends in the school cafeteria.
We've all seen it.
It's fast, sure, But the consequence is that it's just filled with bias.
Because your friends, or the first 10 people you see, probably share a lot of the same opinions and backgrounds as you.
You haven't randomly selected anyone. You've just grabbed the closest people.
And trying to apply their opinions to the entire school, that's a huge mistake. The results just can't be generalized.
It just doesn't represent the world outside that one cafeteria table.
And that risk of bias leads us right into the science of accuracy, specifically the numbers game.
Sample size.
Sample size, it's crucial. I mean, if you only ask 5 people what they think, you're not going to have a good idea of what millions think.
Makes sense.
So generally, a larger sample means more reliable data. But here's the part that always surprises people.
What's that?
The sample size doesn't actually have to be enormous.
Wait, stop. The United States has over 330 million people. You can't tell me you don't need millions of people in your sample? That sounds impossible.
I know it sounds like a magic trick, but it's just statistics. Researchers have found that for national surveys, a sample of about 1,000 people.
Just 1,000.
Just 1,000 people is often enough to accurately represent the entire population of the United States.
How is that even possible?
Because the goal isn't just quantity, it's the quality of the selection. As long as those 1,000 people are picked using a really rigorous random method, they act like a tiny, perfect mirror of the whole country.
So adding more people after that point doesn't help much.
It doesn't increase accuracy by much, but it definitely increases the cost.
But the biggest danger, the thing that ruins everything, is what you mentioned earlier, sampling bias.
It's the silent killer of good data. It happens when certain members of the population are just more likely to be selected than others.
So the sample doesn't actually reflect the group you're studying.
Even if you thought you were being random.
Can you give me a real-world example? How does that sneak in?
Absolutely. Imagine a researcher wants to survey Americans about their health habits. They decide to do it over the phone, but they only call landlines.
The old phones plugged into the wall.
Right. Who mostly uses landlines today? It's generally older populations, maybe people in more rural areas.
So you're missing all the younger people in cities who only have cell phones.
A massive group. You've automatically biased your results to reflect an older, more rural America, not the entire country.
So the ultimate mission is to create a representative sample.
That's the goal. The small group has to look and act just like the big group.
If the population is 50% male and 50% female, the sample has to be 50-50.
If 20% of your population lives in cities, 20% of your sample must live in cities.
And when you get that match, you unlock the big prize. Generalization.
That's the word.
Generalization means you can confidently take the findings from those 1,000 people and make solid predictions about how millions will behave. That's why polls work.
But because no sample is ever truly perfect, I mean, it is only the 1,000 people, we always have to talk about the margin of error.
This is the number you always see flashing underneath poll results on the news, right?
Right.
What is it actually telling us?
It's basically the researcher being honest about the uncertainty. It's the amount of wiggle room they need because they didn't talk to everyone.
Like a safety net?
Exactly. So if a poll says 60% of people like a movie with a 3% margin of error, it means the true number is probably somewhere between 57% and 63%.
So a smaller margin means the results are more precise.
Much more precise. If you see a margin of error of, say, 10%, you really shouldn't trust that main number very much. It's just too broad.
Okay, so let's talk about logistics. What if your population is spread out all over the place, like trying to survey every 8th grader in Texas? You can't send people to hundreds of different towns.
You can't. It's just too expensive. And that's why, for efficiency, researchers sometimes use cluster sampling.
Cluster sampling.
Instead of picking random individuals from everywhere, researchers divide the huge area into smaller geographic clusters like towns or counties or maybe specific school districts.
So they're grouping people by location first.
Yes. Then they randomly select just a few of those clusters. And here's the key part. They then study everyone within those chosen clusters.
So they don't have to visit every corner of the state, just the few areas they picked?
Right. It's much cheaper and easier than trying to track down one student in Dallas and another in El Paso.
But I'm guessing there's a drawback.
There is. It can be less accurate if the few clusters you happen to pick are really different from the ones you didn't. If all 10 counties are wealthy suburbs, your sample is going to be biased.
It's a trade-off between cost and precision. Okay, so we've got our sample. We know how to measure its accuracy. How do you actually get the information from them?
Usually with surveys. A survey is just a list of questions, whether it's online, on paper, or over the phone. But the survey itself is another place where error can creep in.
You'd think writing questions would be easy.
It's fascinating how carefully they have to be written. If a question is unclear or if it sort of guides the person to an answer, you can mess up the results.
What do you mean guides them?
Well, if I ask, do you support the highly effective taxpayer-funded playground renovation program? I'm kind of pushing you to say yes.
Ah, I see. You've already loaded it with positive words.
The questions have to be neutral. They have to be unambiguous, meaning they can only be interpreted one way. Otherwise, the question itself changes the answer.
So why should you, the student listening, care about all this? Because it affects your daily life in ways you might not even realize. Think about the media you consume. TV networks use sampling to see which shows are popular. That decision about what gets canceled is based on a tiny fraction of viewers.
In health, it's even more critical. Medical researchers test new medicines on a small representative sample to see if they're safe for everyone. That little sample protects millions of people.
And in business, companies use it to test new snacks before they make millions of them. Even in factories, they use quality control sampling.
They don't check every single phone coming off the assembly line.
You just check a few from each batch to make sure the whole run is good. That's how we get reliable products.
It's everywhere.
Sampling is this powerful, essential tool. And understanding the difference between good, random sampling and that risky convenience sampling helps you become a much smarter citizen. So the next time you see a headline that says 60% of people agree, ask yourself a few questions. Who was their target population? Was the sample truly random? And most importantly, what was their margin of error? Don't just accept the number. Understand what's really beneath it. Good luck with your studies.